Here's solutions to the final for ECE 320 for fall 2022. The first problem is a load line problem. Given the diode, draw the load line for the following circuit and solve graphically for the voltage and current. Now for the load line, I want to find the intercept on the x-axis and y-axis. On the x-axis, the current is 0. So to make the current 0, just open this up, find the voltage, and I get by voltage division R over 1000 plus R times 10 volts, 5.857 volts right here. On the y-axis, the voltage is 0. So take these 2 points and short it, makes it 0 volts. I get 10 volts over 1000 ohms, 10 milliamps. 2 points determines a line. The intersection is the solution. So this will have roughly 2.4 volts, 5.5 milliamps flowing across it. Problem 2 is write the equations for the following circuit. They're nonlinear, hard to solve. If I did want to solve, I'd have to use fmin search. Let's see. But here you don't have to solve. The trick is, first for the diodes, write the voltage anode to cathode. So if the first diode sees V2 minus V1 anode to cathode, that goes in this equation. That's your VD, anode to cathode. The second diode, VD, is V1 minus V3. The third diode, V4 minus V1. So the three equations for the diodes would just be the voltage anode to cathode, V2 minus V1, V1 minus V3, V4 minus V1. Gives you the currents ID1, ID2, ID3. Then the voltage node equation is at node 1, the sum of the current from the node equals 0. So the current left plus the current down plus this current plus this current plus that current, that's everything. That's got to be 0. That's your V1 minus V0 over R plus V1 minus V2 over 2K minus ID1 plus ID2 minus ID3 equals 0. At node 2, let's do that one in orange. The current up, current down, current right equals 0. That's V2 minus V1 over 2K plus V2 minus V3 over 3K plus ID1 equals 0. Third equation. Let's do that one in green. Current up, current down, current right equals 0. V3 minus V2 over 3K plus V3 over 4K minus ID2 equals 0. And the last equation is right here. Current down, current up equals 0. ID3 plus V4 over 5K equals 0. Gives you 7 equations, 7 unknowns. Problem 3 looks at an ideal diode. Assuming these are ideal diodes, now find the voltages and currents. The trick with an ideal diode is to figure out which ones are on, which ones are off. If they're off, the current is 0. If they're on, there's a 0.7 volt drop, anode to cathode. So I'm trying to push 10 volts, it's trying to push current this way. This diode is probably off, current's going backwards. This diode is probably off, current goes backwards. This one's probably on, so this is a 0.7 volt drop, meaning whatever V1 is, this is V1 minus 0.7. That's it. Now it's just a circuits problem. Find the voltage. To do that, I actually have just one unknown. I need one equation for one unknown. I'm going to draw a supernode. So I've got resistors coming out, sum the current to 0. This current, which is V1 minus V0 over R, plus this current, V1 minus 0.7 over 4K, plus this current, which is 0, equals 0. So I've got my one equation, one unknown solved. V1 is 7.571 volts. V3 is V1 minus 0.7, 6.8 volts. A couple of ways to get V2. By superposition, it's something times V3 plus something times V1. The gain times V3 is by voltage division 2K over 5K, 2/5 of V3 from V1, 3/5 of V1. That's one way to do it. 7.29 volts. And V4 is 0. The current right here, that one's a little bit tricky. One way to do that is conservation of current. It's the current in equals current out. So this current I can calculate. It's 10 minus V1 over R. This current I can calculate. That's B1 minus B2 over 2K, or B1 minus B3 over 5K, either one. This current is 0. This current I don't know. They got to add up. So this is whatever is left over. And that gives you 1.578 milliamps. Problem 4 is an AC to DC converter. Given this circuit, where I've got 30 volts coming in, find the voltages and currents, DC and AC voltages actually. DC voltage, V1 charges up to charges and discharges. The peak is going to be 30 minus 0.7, 29.3 volts. To find the drop, find the current. The current here is 29.3 over 100 plus R, roughly, worst case, 19.35 milliamps. From I equals C dV dt, I know this current is 19.35 milliamps, worst case. I know C, I know dt is 1/60th of a second, solve for dV, and dV is 6.45 volts. So this is what V1's doing. It charges up to 29.3 volts. And it drops, that's your peak-to-peak ripple, 6.45 volts. The DC level then is the peak minus half the ripple, 26 volts DC. And once I know the V1 DC, I can find V2 DC is just R over R plus 100 times V1, 24.35 volts. For AC analysis, I know the ripple is 6.45 volts peak to peak. At 60 hertz, I can find the impedance of the inductor, J 1885 ohms, find the impedance of the capacitor, minus J 663 ohms. These two in parallel gives you 254 minus J 543. Now voltage division, R1 over R1 plus R2 times Vn. Take the magnitude, that's the ripple at V2. Problem 5 is design a clipper circuit. Initially the slope is 5, drops to 1.5, drops to 0.5. The first zener turns on at 5 volts, second turns on at 8 volts. So now right away, this is a 5 volt zener. This is an 8 volt zener. The initial slope of 5 says that 1 plus the ratio is the gain. This must be a 4K. Gives you a gain of 5. By voltage division, the gain drops. I want the gain to drop from 5 down to 1.5 to solve for R1. So that'll be the voltage division, R1 over R1 plus 1000 times a gain of 5, gives you 1.5. Solve for R1, get 428 ohms. These in parallel. The gain drops to 0.5 when both zeners turn on. When they both turn on, R1 is in parallel with R2. Call that R1, 2. Voltage division times 5 is 0.5. Solve. The parallel resistance is 11 ohms. I know R1, solve for R2. R2 is 150 ohms. So that's what you should get for problem number 5. Problem 6 is a transistor and a load line. So given the blue line, the VR characteristics, find beta. And that's just the ratio. 5 milliamps produces 125, that's 25 to 1. 4 milliamps produces 100, 25 to 1, 25 to 1. Beta is 25. For the load line, the x-intercept is at 20 volts. The y-intercept is 20 over 150, 133.3 ohms, or 133.3 milliamps. 2 points gives you a line. To find the operating point, find the base current, Vn, this is going to be 0.7 volts. Again, this is a diode, 0.7 volt drop across the diode, over R gives you IB. IB times, or IB is 3.04 milliamps, times beta gives you 76 milliamps. That's the current that I'm commanding. Where that intersects my load line is my solution. So my solution is right here, 8.5 volts, 76 milliamps. That's problem 6. Problem 7 is design a Schmidt trigger so that it turns on at 2000 ohms, turns off at 2200 ohms. So R is from my birth date. If it's 1414 ohms, I can find the voltage at this point. It's going to turn on at 5.8 volts, off at 6.0. See, this is where it turns on. I think it looks like this. So it turns on at 5.8 volts, turns off at 6.08. When it turns on at a lower voltage, connect to the minus input. Where the output goes high is the offset, 5.8 volts. And the gain is the ratio. Output changes, in this case I got a 5 volt power supply. Output changes by 5 volts. As the input changes by that difference, gives you a gain of 21. Pick this to be 21 to 1. For the output to drive the LED, if this is 50 milliamps, and this is 3 volts, this is 0.2 volts, 10 minus 3.2 over 50 milliamps is 136 ohms. This has to saturate it. So if this is 50 milliamps, this has to be at least 0.5 milliamps. Less than 25 milliamps, because that's all a 602 can do, pick a number between 0.5 and 25. I chose 4.3 because then 5 minus 0.7 over 4.3 milliamps is 1K. 1K resistor works at the base. Actually, anything between 172 ohms and 8,600 ohms works. Problem 8 is this is actually 3 NOR gates. So if I have the first NOR gate, second NOR gate, 2 NORs go together, gives you another NOR gate. Here's your logic. That's what this is implementing at the transistor level. Find the voltages and currents. Well, the first, I've got 5 volts going to ground, so that's going to be 5 minus 1, 2, 3 diodes, 5 minus 2.1 over, this is 1414 for me, over R, gives you 2.05 milliamps, and this one saturates. V1's 0.2 volts. Down here, I've got 0 and 0. That makes this 0. This one's off. On the right-hand side, I've got 0.2 volts. That's not enough to turn on these diodes, so this turns off. I've got 10 volts. That is enough to turn this on. So the current is going to be 10 minus 1, 2, 3 diodes, 10 minus 2.1 over R plus 200. The resistors in series gives you 4.8 milliamps. That allows 489 milliamps to flow. I'm only trying to push 5 milliamps, 50 milliamps. Beta IB is more than IC. This saturates, 0.2. And then to find V2, it's 10 minus I times R. Gives you 9.2 volts. And that's kind of called loading. Normally this is 10 volts. When I connect it up to something, the voltage drops. That's loading. Problem 9. If you have this MOSFET, find the transconductance gain, K sub n. Draw the load line, find the operating point when VG is 7 volts. Well, to get the transconductance gain, pick a point, like right here. When VGS is 9 volts, the current is roughly 270 milliamps. The threshold voltage is 3 volts. Solve for K sub n, I get 0.015. Here's K sub n. The load line, when the current is 0, the voltage is 10 volts. That's this point on the load line. When this is 0 volts, 10 over 45 gives you 222 milliamps. That's this point. 2 points determines a line. Where it intersects with the VGS equals 7 volts is your solution. 4.6 volts, 120 milliamps. And the last problem is design a CMOS logic to implement this gate, or CMOS logic to implement that Carnot map. So I'm going to circle the zeros. That's kind of my preference way to do it. You can circle the ones too. If you circle the zeros, you get the logic on the low side. So that's going to be B or A bar C bar or AC. On the low side, Y bar, when these are true, I'm pulling it low, so that's what I'm implementing. That's using N-channel MOSFETs. That's going to be B or A bar and C bar, or A and C. Series is and, parallel is or. That's the low side. The high side is De Morgan's law. Series becomes parallel, parallel becomes series. So this is B and parallel with, that becomes in series with A and parallel with C, and in series with A bar in parallel with C bar. So this implements that logic. And that's the final for ECE 320.